All right, grab a seat, everyone. Let's get started. Welcome to Astrobiology 101. I'm your lead astrobiologist. And today, today's explainer is going to tackle humanity's absolute most profound and honestly most terrifying existential mystery. We're going to look up at the night sky not just with awe, but with rigorous analytical math to ask the ultimate question about our place in the cosmos. Let's kick things off with just the sheer scale of our own neighborhood. The Milky Way contains up to 400 billion stars. Now, that is a number so staggeringly huge that if you started counting just one star per second, it would take you literally 100 lifetimes just to count them all in our galaxy alone.
And remember, our galaxy is just one tiny speck. The observable universe is roughly 90 billion light-years across, holding at least 100 billion galaxies. Within that vast, expanding ocean, there are probably trillions upon trillions of habitable planets. So looking at those numbers, I really want you to ask yourselves, are we actually the only living things out there?
To figure that out, here's our syllabus for today's explainer. We'll start with the scale of the cosmos, move into the Drake equation, unpack the speculative variables, confront the Fermi Paradox, and finally, discuss the Great Filter.
Okay, part one, the scale of the cosmos. Are we living in a crowded universe?
To really get astrobiology, you've got to wrap your head around deep time and deep space. In the Milky Way alone, we're talking about 20 billion sun-like stars. Estimates suggest that a fifth of them have an Earth-sized planet sitting right in the habitable zone. You know, that perfect Goldilocks area where liquid water can exist. Now, do the math with me. If only 0.1% of those habitable planets harbored life, there would be 1 million planets with life just in our Milky Way. Plus, the Milky Way is about 13 billion years old, while Earth is only 4 billion years old, meaning there have been trillions of chances for life to develop in the deep past, long before Earth even existed.
Which brings us to part two, the Drake equation, and how we formulate this search.
So how do we actually calculate this probability? We don't just guess blindly in astrobiology class, we use math. Formulated back in 1961 by Frank Drake, this equation was designed as a systematic way to evaluate all the specific probabilities involved in alien life existing. We use it to estimate n, which is the number of technologically advanced detectable civilizations hanging out in the Milky Way right now.
What's really fascinating here is how this equation breaks down the birth of an alien civilization step by step. It's kind of like a cosmic funnel. We start big, with the rate of star formation. Then we narrow it down to the fraction of those stars that actually have planets. Then the number of those planets suitable for life. Next, the fraction where organic life actually appears. Then, where that life becomes intelligent. Next, the fraction that develops detectable spacefaring tech. And finally, L, the length of time those civilizations survive and broadcast signals into the dark before going extinct or just going quiet. Let's move to part three, the speculative variables, or what I like to call the illusion of certainty. On the surface, the Drake equation looks incredibly precise. But here is where we hit a massive scientific wall. Thanks to modern astronomy and telescopes like Kepler, we actually have highly accurate empirical data for our knowns, like star formation rates and exoplanets. But when we look at the unknowns, those biological and sociological variables, they remain highly, wildly speculative. Why? Because we simply lack the scientific mechanisms to understand them. We literally do not know the exact mechanisms of how life starts from non-life, how you jump from single cells to complex brains, or what the actual odds are of a civilization destroying itself. And this leads to a severe problem in our field, the overconfidence effect. Because we don't truly understand the mechanism of abiogenesis, how inanimate chemistry suddenly becomes biology, scientists are essentially just guessing. When optimists plug their hopeful numbers into the Drake equation, they calculate millions of active civilizations out there right now. But when pessimists plug their numbers in, the result is often less than 1, implying we are an absolute, total cosmic fluke. Now for part 4, meeting the Fermi Paradox. This is the ultimate reality check. We have a stark collision between theory and observation here. If the optimistic math suggests a crowded universe, our physical observations demand a harsh reality check. Just consider the timeline of interstellar expansion. Even if a civilization didn't have magical warp drives, but just used generation ships traveling at a slow, achievable pace, it would only take them between 2 to 50 million years to completely traverse and colonize the entire Milky Way.
In geological terms, 50 million years is absolutely nothing. The dinosaurs died out 65 million years ago. So a civilization that started a billion years ago should have easily colonized every single star system by now. Which perfectly leads us to the physicist Enrico Fermi. Picture this. It's 1950. He's on a lunch break at Los Alamos National Lab, chatting about the vast probabilities of life with his colleagues. And suddenly, Fermi just blurts out this exact frustrated question, but where is everybody? That single question birthed the Fermi Paradox. It's the conflict between the incredibly high probability that intelligent life is everywhere and the absolute total lack of physical evidence that any other civilization has ever existed. It's the great silence. If they've had billions of years to spread, the universe should be teeming with spaceships, megastructures, and radio signals. Yet, we see and hear absolutely nothing.
So, part 5, the Great Filter. How on earth do we resolve this paradox?
If life is assumed to be common, but we see zero evidence of it, there has to be a barrier that's incredibly hard to overcome. Back in 1996, Robin Hanson proposed this concept called the Great Filter. It represents some natural phenomenon, some impossible evolutionary hurdle that stops species from progressing to the point where they can spread across the stars. It quite literally filters them out of existence.
And here is the question that keeps astrobiologists like me awake at night. Where is this filter located in the timeline of a species? Is the Great Filter behind us, meaning the leap from non-life to single cells, or the leap to complex cells is so impossibly rare that we are one of the only species to ever make it? Or does the Great Filter lie terrifyingly ahead of us, meaning life evolves to our level all the time, across the galaxy, but they inevitably hit a wall, like technological self-destruction, and get wiped out before they can ever leave their star system?
Astrobiologists have proposed tons of other fascinating resolutions to this, too. The die-off scenario suggests energy-hungry civilizations inevitably cause massive climate change, collapsing their own ecosystems. Or maybe there's an oxygen bottleneck. A planet might have complex life, but lacks the exact atmospheric oxygen needed to invent fire and metallurgy, permanently trapping them in the Stone Age. Then there's the grabby aliens theory, suggesting loud, aggressive civilizations expand fast and suppress everyone else, and we just haven't noticed them yet. Or even the zoo hypothesis, the idea that advanced life does exist, but they are deliberately quarantining Earth to let us evolve culturally on our own, kind of like a cosmic nature reserve.
But no matter how many creative theories we come up with, they all bring us crashing right back to the stark empirical reality we face today. We have absolutely zero evidence of life besides us. When we look out with our absolute best telescopes, the universe appears to be empty and dead. No one is sending us messages, and no one is answering our calls.
So are we completely alone, trapped on a tiny, moist mud ball in a cold, eternal universe? I want you to really think about that. Does that thought scare you, class? Good, because if it does, you are having the exactly correct emotional reaction. The weight of this realization should be profound.
Because if those highly speculative variables we discussed earlier mean that the jump to complex, intelligent life is impossibly rare, well then humanity's role in the cosmos shifts dramatically. We might just be the sole torchbearers of intelligence in the entire galaxy. If we let life on this planet die due to our own self-destruction, there might literally be no intelligence left in the universe. We have an immense existential responsibility to survive, to overcome whatever great filter lies ahead, and to keep this incredibly delicate flame of consciousness alive. So I'll leave you with this final, truly provocative thought. As you walk out of class today and look up at the stars tonight, I want you to ask yourselves, based on everything we've covered, are we the fragile dawn of galactic intelligence or the flickering end of it? Class dismissed.